Hello there, and welcome to the second lecture as part of this quantum field theory course. So in the first lecture, we looked at classical physics, classical mechanics in particular, and we introduced this Lagrangian and Hamiltonian formalisms of classical mechanics. In this lecture, we're going to continue thinking about the classical world, but rather than thinking about mechanics, we're going to think about classical fields. So classical fields, classical field theory is the topic of this second lecture. Okay, so let's begin thinking about classical fields, and let's begin by thinking about a simple question. What is a field? We should get this idea clear on our head before we start to look at quantum versions of fields. Okay, so here's one definition of a quantum field. Here's one definition of a field that I can give you. Okay, so given a position, so given some coordinates, in other words, in space and time, I can tell you what a field does. So what a field does is that it outputs an amplitude. Okay, so in other words, I put in some coordinates and it gives me out an amplitude or some number at that position, at the coordinates that I give you. And of course, there's many examples you will have met of classical fields. You can think of many. Here's a few that come immediately to mind for me. So one is the temperature in a room. Obviously, this can vary across the room. So as you go closer to a window, it may be colder. As you go to the radiator or heater, it'll warm up. And this is an example of a scalar field. Okay, so the thing, the amplitude that gets returned is just a number, a scalar quantity. But there's other types of fields you've met in physics which are not just scalars. I guess the most obvious example to think about are electric or magnetic fields. Okay, so again, so given some coordinates, so given some point in space and time, the field tells you about something at that position, but for electric and magnetic fields, the thing that it tells you about is a vector quantity. So it tells you about the three coordinates, the three values of the electric field, for example. So Ex, Ey, or Ez. And then there's a whole bunch of other examples you could think about. So the gravitational field is another obvious example. Gravitational field is interesting, I guess, because you can just think of it in a couple of ways. So I mean, you could just think about it in terms of the scalar potential phi, gravitational potential at some point. Or if you're thinking about general relativity, I have a tensor object, so the metric, which is now a tensor. So those are all examples of fields, and of course fields are not usually static. Okay, so they can change. As I said, they can change. So the temperature can change as you walk across the room, and it can also change as a function of time. So it's going to usually be colder at night than it is during the day. So in general, the dynamics of the field, the fact that the fields can change, are described by the field equations. Okay, so dynamics. The dynamics are described by field equations. So the field equations are obviously important then to understand, how things change as functions of space and time. And you've met a whole bunch of field equations in your life, I'm sure, right? So the famous ones are Maxwell's equations. Got the divergence of E. Tells us about how E varies in space, given some charge density at some point. You get similar equations for the magnetic field and so on. Well, we don't need to rewrite all of Maxwell's equations, but those are just some examples of field equations that you have met before. Okay? So, as an undergraduate, you will have gone through some procedure, some arguments as to where Maxwell's equations come from. Sort of build them up from some underlying principles, Coulomb's law, and so on. But it turns out there's a very elegant way that you can derive these field equations. Okay, so and that's similar to what we did in classical mechanics. Okay, so just as in classical mechanics, our equations of motion could be found from a Hamiltonian or a Lagrangian. we're going to find that our field equations are the equations that tell us how the fields change in space and time. These field equations can also be found from a Lagrangian and from a Hamiltonian. This is a nice feature of Hamiltonians and Lagrangians. As I said, they can be generalized in a way that Newton's laws cannot. So I know Newton's laws of mechanics, but I don't know how to go from Newton's laws per se to the field equations. Well, it's going to be relatively trivial to go to write down a Lagrangian for the field and to find out what its field equation should be. Okay. So I'm going to go through and turn then the concepts required to describe the classical fields. So we're going to look at the Lagrangian density, we're going to look at the Hamiltonian density, and see how we get dynamics of fields from those things. So that is where we're going in the rest of the lecture. Okay, so I want to start here by describing a new concept, which is the Lagrangian density. I put density in brackets here because, as we'll discuss, often the term density is dropped and people simply talk about the Lagrangian density as a Lagrangian. But in principle, as we'll see, there is a separate quantity, which is the density quantity. Okay, so what happens in classical field theory? So what we have is we have fields, okay? And in classical field theory, we can construct a Lagrangian, which is going to be a function of my fields. So we're going to have a Lagrangian. Okay, and so in classical mechanics, we saw that our Lagrangian were a function of the coordinates and the derivatives of the coordinates. So in classical field theory, the Lagrangian is going to be a function of the fields. Let me write the fields as phi. Phi can in general depend on spatial and time coordinates. So it can depend on the field, and it can also depend on the derivatives of the field. So in this case, we're going to consider both the time derivative, phi dot, to be d phi dt, and on the spatial derivative, let me write it as the gradient of phi in this case, x and t. Okay, so we're going to construct a Lagrangian, and it's going to be a function of these field quantities. So in these lectures, we're only going to consider one class of fields, and that is the class of scalar fields. Of scalar fields. Okay. So in general, in particle physics, there are other types of fields that you're interested in. So there's vector fields, which describe the photon and the W's and the Z's. And there's spinor fields, which will describe all of my matter particles, so all of the fermionic particles. But dealing with spinors and dealing with vectors adds in extra complexity. So we're going to restrict ourselves to the simplest type of field to study, which is the real scalar field. Oops. We're going to make that simplification because we only have 10 hours together. But much of what I do say about scalar fields can be taken across to describe vector fields for the photon and spinor fields for the matter particles with some extra things that you have to add on top. We'll only consider, and we're going to restrict it even further. In fact, we'll only consider real scalar fields. Okay, so you can also have complex scalar fields. But well, at least at the start anyway, for the first few lectures, we're going to simply talk about real scalar field, simplest thing that you can imagine. Okay, so for this class of real scalar fields, the Lagrangian is going to take the following form. Okay, so we introduce the Lagrangian L, and it's going to, in fact, end on another quantity, which is this Lagrange density, or Lagrangian density. Okay, so it's a density here because we have to integrate it over volume to get to the we integrate the Lagrange density over volume to get to Lagrangian. And in general, this Lagrange density depends on the fields, as we said, and also on the derivatives. Let me write the derivatives using this 4-vector notation as d mu phi. Okay. This is our quantity which is going to be important, so this curly L. This quantity is the Lagrange density or the Lagrangian density. Different books call it different things. But in practical terms, I've never heard it. When people talk about it, they simply call this the Lagrangian. Okay, so they drop the fact that it's a density because it's clear from the context what it is. Okay. So we're going to use a principle of least action again to go from the Lagrange density to the equations of motion. So I should define or remind you again what the action is. The action in this case is in fact defined in the same way as we did before. So it's the time derivative of this Lagrangian. And now I can substitute in for the definition of the Lagrangian in terms of the density, the Lagrange density, and this measure, this dt d3x, is normally combined into simply a d4x. Have that you find the action by doing the 4-dimensional integral of the Lagrange density. Okay, so as I said, the equations of motion follow from the principle of least action. So the principle of least action is where we demand that delta S is 0. We demand that this principle holds. We end up with some equations that the Lagrange density must satisfy. So again, in these videos, I'm not going to derive what that equation is. They should have been derived for you in the pre-lecture notes. If you want to see the full derivation, please refer to those notes. Let me just quote the end result. The end result, the important result we're going to use is that the partial derivative of the Lagrange density with respect to the field phi satisfies the following equation. So we have d mu, have another partial derivative. It's the partial derivative with respect to d mu phi. So this is our Euler-Lagrange equation for the fields. In this example, it's the Lagrange density, this curly L, which enters, and rather than doing partial derivatives with respect to coordinates, we're now doing partial derivatives with respect to the field and with respect to the derivatives of the fields. So next we'll go on and we'll look at an example of using this Euler-Lagrange equation in a specific case. Okay, so I've introduced the Lagrange density, or simply the Lagrangian as most people call it. And we've also seen what the Euler-Lagrange equation is, which will allow us to get the equations of motion for the fields. So let's actually use or consider a specific example and see how we go from a Lagrange density to getting the equations of motion. So the example we're going to use is going to give us the Klein-Gordon equation. Okay, so I want to show you how you can derive the Klein-Gordon equation from a Lagrange density. Okay, so let me write down what the Lagrange density is in this case. Okay, so we said it's going to depend on the fields and on the derivatives of the fields. Let me just write something down and we'll discuss it. So we have a half d mu phi, and we obviously have to contract our indices, or we should contract our indices in this way, okay, so that we end up with a scalar quantity. And let's manipulate this in a couple of ways, which will be useful later on. So we can write this as a half, and we can use our metric eta nu mu, which just has 1, minus 1, minus 1, minus 1 along the diagonals. We'll write it with only sign indices on the derivatives. And if we put in what eta nu mu is, we put in the fact that this is 1, minus 1, minus 1. If you put along the diagonals, we'll get that this is a half the time derivative of the field squared. I'm going to pick up a minus from the minus signs in the in eta. Half the gradient squared minus a half m squared. I can see I'm missing. It should be m squared phi squared. Sorry. But it's phi squared, but it's also m squared phi squared. Okay, so there's some properties of L that this Lagrangian, this Lagrange density has, and which, in fact, all of them, all Lagrange densities should have. First of all, this should be real. So in this case, this is sort of trivially satisfied because we're working with real scalar fields. Okay, so our fields are real, satisfied trivially in this case, but in more complex scenarios, we must arrange it so that L is a real function. We must have that L must be a Lorentz scalar. At least if we want our theory to be consistent with special relativity. And so we have arranged for that to happen here through the way that we have contracted our indices. Okay, so we have from the top line, it's the Lorentz. The fact that this is Lorentz, that this is a Lorentz scalar is kind of just manifest. I guess it's less obvious if you look at this form, but this is, of course, the nice feature of 4-vector notation. And it's maybe not so obvious to you here, but in fact, in this example, L is still of the form where it's a kinetic energy minus a potential energy. I should be a little bit more careful. It's the Lagrangian is still of the form of T minus V. So the Lagrange density leads to that form. A little bit more careful. So remember, L is the integration over the volume of the Lagrange density. In fact, in the example above, we have that the kinetic energy is, we need to integrate our Lagrange density over this volume factor. So our kinetic energy is this first term that we see. So it's a half phi dot squared. And our potential are these bits that come with the minus sign. So that's our minus V are these terms. So V, E3x, a half grad phi squared plus a half m squared phi squared. So very soon, later in this lecture, we'll see how you can find out what the energy is using the energy momentum tensor for a general field theory and how you can calculate it from the Lagrangian. Okay, so we have this Lagrange density above. I said one of the nice things is we can work out what the equations of motion are, what the field equations are, using the Euler-Lagrange equations. So let's do that. Let's derive these field equations. Okay, so it's going to be useful to start with this second form that we had above for the Lagrangian. So let me just write it down below again. That we have it. We had a half, and we had the derivatives of the fields, and then we subtracted off half, and I'll remember the square this time, m squared phi squared. And we're going to use the Euler-Lagrange equation, which is dl d phi is d mu dl, and this combination of the partial derivatives. So we need to take the partial derivatives of our of our Lagrangian with respect to the derivative and with respect to the field. So let's go ahead and do that. So dl d phi is the easier one to calculate. It's relatively straightforward. So our first term in the Lagrange density does not depend on phi. It only depends on the derivatives. Phi only enters into the second term. So we have minus m squared phi when we do the differentiation. That was easy as promised. And then the second one we have to do is what's on the right-hand side of the Euler-Lagrange equation. So let's go ahead and do that as well. We'll do dl mu phi to begin with. Okay. It's just a case of using our rules of differentiation. It's actually going to be perhaps easier to change the index here. Let's call it rho. Since I've used mu and nu in my Lagrangian, let's call this rho, okay? And then, in other words, I want to change both of the indices in my Euler-Lagrange equation to be rho. So I can do this because these are dummy indices, they're just summed over. As long as I use the same name, I can call them whatever I want. But it's best not to call them the same name as letters which appear elsewhere in your equation. So let's call it rho. I'll do the derivative with respect to rho. So what do we get when we do this differentiation? So when we differentiate this first term with respect to d rho phi, find this Kronecker delta symbol, okay, which is 1 if rho and mu are the same, and it's 0 if rho and mu are different. We still have the other derivative of the field using this differentiation rule, doing each term one at a time, and then in the second one we'll get Kronecker delta rho nu. So again, it's 1 if rho is equal to nu, and it's 0 otherwise. So we can tidy up this expression a little bit. So let's do that. So we have a half. So what's going to happen? This obviously sets rho equal to mu. So anywhere we have a mu, we should replace it with rho. We have the first term, then we have this. Then we can also do it on the second term. So we're going to, in the second term, this tells us to replace nu with rho phi. And then, of course, our metric, this eta symbol, I can use it to raise and to lower indices. And of course, it's symmetric. So eta rho nu is the same as eta rho nu. So the order of the indices doesn't matter. It's a symmetric function. Okay. Let's use that to raise both indices. So I get a d rho phi plus a half d rho phi. In other words, I just get d rho phi. Okay, so that's what I get when I differentiate this Lagrange density with respect to d rho phi. Okay, so I just end up with the derivative of the field. Good. So when I plug this into the Euler-Lagrange equation, I plug it into this equation, I must have that minus m squared phi is d rho. Got this d rho, and then I can substitute in for the term that I've just found. So I've just done this differentiation here. D rho with an index down, d rho with an index up, and here's final field equation. So this equation, hopefully you'll recognize, hopefully you've seen it before. This is the famous Klein-Gordon equation. This is the field equation for this particular, that follows from this particular Lagrangian. Okay, so this is often written both terms on the same side, and we set it equal to 0. So of course, the Klein-Gordon equation, many of you will know that it was in fact first written down by Schrödinger. Schrödinger considered it as as an equation for hydrogen, and he didn't stick with it because it doesn't quite predict the correct energy levels for hydrogen. So if you try to interpret this as kind of a relativistic version of the Schrodinger equation, it doesn't quite work because fine structure doesn't work out in detail. Schrodinger abandoned it as an equation that describes hydrogen. Of course, other people tried to describe, tried to use it as a relativistic generalization of the Schrodinger equation. So if you try to interpret this phi as a wave function, people ran into some conceptual difficulties because it turns out that if you try to interpret this as a wave function, you end up with both negative energy solutions and negative probability solutions. So trying to just interpret this as an equation, as a quantum equation in the way that you would interpret the Schrodinger equation leads to all sorts of. But quantum field theory is going to show us how to actually quantize this theory correctly. Okay, so let's see. We're going to see the correct procedure for quantizing this theory. How we can do this consistently. So it's not, this is not already a quantum theory in the way that the Schrodinger equation is. Okay, we have to do much more. We have to introduce this quantum field theory formalism basically to consistently quantize this theory of the real scalar field. And quantum field theory, thankfully, does not have these issues that people ran into of negative particles, negative energies, sorry, and it doesn't have this issue of negative probability densities that you normally run into. Okay, so that's one example of how you can use the Euler-Lagrange equations in this field, in this classical field theory formalism, to go from a Lagrange density to an equation of motion. So we've looked at this famous Klein-Gordon equation. So we've seen that one nice feature of the Lagrangian is that we can use the Euler-Lagrange equations to figure out the field equations, the equations of motion for the field. Let me discuss a second really nice thing you can get from the Lagrange density, and that's the so-called energy momentum tensor. So let me write down what it is, with the indices up actually. So this tensor, calculated from the Lagrangian by taking derivatives of the fields, and then we subtract off the Lagrangian, and I need to have my indices up, so they're up. So this product, this combination of factors, is the energy momentum tensor. So this is a nice quantity because it leads to a conserved current. So this is actually three equations. So you'll notice I've repeated indices mu, but eta is free here. So eta takes the value of 0, 1, 2, and 3. So I get four separate conserved equations. And this is related to the energy and the momentum as follows. So we get the energy by integrating t00 over t3x, and we get the three components of momentum by integrating t0i over d3x. So t is symmetric, so you can do t0i or ti0, you will get the same answer. Okay, so how do we actually go about constructing what this energy momentum tensor is? Well, in order to do that, you can use a very nice theorem called Nernst's theorem. Okay, so this is a theorem that provides general way to relate conservation laws. Okay, so this is what we have above. This is a conservation law. We're relating conservation laws to symmetries. Okay, so the statement of Nernst's theorem is that every continuous symmetry spell symmetry. Symmetry has two M's, yeah. Every continuous symmetry gives rise to a conserved current. So if I have two continuous symmetries, I'll have two conserved currents. If I have 4 conserved symmetries, I'll get 4 conserved currents, and so on. Okay. What does this word mean? What does it mean to be a symmetry? So let's define what that is. So an operation is a symmetry in my theory if L is unchanged, or I can relax it a little bit, or L can change by a 4 divergence. Write down explicitly what a 4 divergence is in a second. Since this leaves the action unchanged. Since leaves the action unchanged. Okay, so remember the field equations follow from the principle of least action. So we wanted the action to be stationary. So the action is an important thing for defining the theory. Okay, so if I have some operation that leaves the action unchanged, I'll end up with the same physical equations of motion. And so it turns out that you can leave the action unchanged if L is unchanged under some transformation, or you don't have to be as strict as that. It turns out that L can change by this 4 divergence. So this is an example of a 4 divergence. Okay, so it's simply some function. Well, this is mathematically what a 4 divergence. So let's look at an example of something that operation that does change the Lagrangian by a 4 divergence, and that's going to be space-time translation. So let's consider a transformation where x prime, where I'm doing constant translations of my space-time coordinates. So here, delta x mu is some, I'm writing it as epsilon to indicate that it's some small shift in my 4 coordinates, so along time and along the 3x directions. So let's think about what happens under my fields with this transformation. Well, I've got a real scalar field here. But to get what the transformation is, I basically do a Taylor expansion. So it's phi x plus the derivative of the field. Field is a function of the 4 space and time coordinates. D mu phi on mu. Okay. In other words, delta phi, the small change in the field, is simply d mu phi times epsilon mu. That's what happens to the field. But we want to think about the Lagrange density, right? So let's think about what happens to the Lagrange density. Okay, so we've said the Lagrange density is a function of the field and also a function of the derivatives of the field, but it's also then going to depend on the space-time points, right? Because my fields are functions of the space-time points. So my Lagrangian must also be a function of the space-time points. And one thing you should remember about the Lagrange density is that it's a scalar quantity. Okay, so it actually transforms in the same way as my real scalar field. Okay, both of these are real scalar quantities. So if I consider how L changes under this transformation, well, L has the same transformation as my real scalar field. Exactly the same, but I replace phi with L. Let me rewrite this slightly. At Lx, I'm going to change this second term slightly and write it in the following way. So I'll have Lagrange density, and then I introduce delta mu nu. So in other words, I'm just rewriting epsilon mu with this Kronecker delta symbol. Now the reason for writing it in this way is to put it in the form that we have above, where we have a 4 divergence. Okay, so now we have something that's starting to look like a 4 divergence. But you'll see that there's a slight difference compared to the above expression, because we actually have 4 continuous transformations going on here. So above, I didn't have any index on my epsilon, while here I do have an index. It's telling me there are 4 transformations. In other words, we know what those 4 transformations are as well. It's simply a transformation through time and a transformation through 3 spatial coordinates. So for instance, one of them is where we set nu equal to 0. Okay? And then we'll also get ones with epsilon 1, get epsilon 2, okay, and so on. Well, the other one's epsilon 3. Okay, so we end up with these 4 expressions where we're just summing over nu. So if we have 4 continuous transformations, all of this form, where it's a 4 divergence, well, Noether's theory tells us every continuous symmetry gives rise to conserved current. So since we have 4 symmetries here, we should expect 4 conserved currents. And those 4 conserved currents are simply going to be the energy momentum tensor. So how do we actually get that mathematical form? Let me quickly show you how you can find that. Okay, so to get the actual mathematical form, we need to consider delta L. Okay, so from assuming that L is a function of my space-time points, we've already shown above that delta L here can be expressed as mu L delta nu epsilon nu. Okay, but we know that the Lagrange density is also a function of the fields and the derivatives of the fields. Okay, so from this second form, we can get another expression for delta L. Okay, so the idea here is to get an expression for delta L only in terms of the fields and the derivatives of the fields, and then we can set it equal to this expression above. So let's go ahead and do that. Some straightforward manipulations we have to do. So let's first of all just write down what delta L is. So it's a function of the field I, and it's a function of the derivatives of the field. Just our expression for delta L. And now we're going to manipulate this a little bit. So one thing we can do is first of all, we should substitute in for what delta phi is. So we actually had an expression above for what delta phi is. We've written it here. So under this transformation that we're considering, we have that delta phi is d mu phi epsilon mu. So let's substitute in for delta phi our expression. It's d mu phi epsilon mu. Okay, so the index is repeated on the derivative and on the epsilon, plus delta d mu phi. Okay, and so here we have something which is delta and a d mu phi, but we know that derivatives commute, so we can rewrite this as d mu delta. If we do that, we then have d mu delta phi, and we know what delta phi is. Substitute in for delta phi. Now this notation isn't ideal, so we have all of these too many mu's going around. So we know that we're summing over these indices together, so it probably makes sense to relabel these. Let's relabel this dummy index to be nu. And let's also do it on the first term as well. So I'm free to relabel these dummy indices as long as they're summing over together. I can call it what I want. So because I already have mu here, let's call it nu to avoid any confusion. Okay, good. Now, there's a trick we can use, which is we can use our Euler-Lagrange equation to substitute for the L d phi. So let's use the fact that the L phi with my Euler-Lagrange equation following. And substitute that into my expression. Okay, so we end up with delta L, L d phi. No, it isn't. I'm substituting in for dl d phi. So it's d mu using the Euler-Lagrange equation. I get this expression times the bit that was left over. Oops, and it should be a nu index I'm looking at this term, so I've got a new index that I have to use. Okay, and then we've got plus L. And I'm going to write the second term to change it ever so slightly. So here I have the epsilon inside the brackets. Okay, but of course, if I differentiate this constant shift, I get 0. So this is, I can rewrite it in this way. Use that the differentiation of this term. So using my my rules of differentiation, I get the following, and because d mu epsilon is this term going to be 0, this is a constant shift, that term overall will vanish. Okay, so that's why these two pieces are just equivalent. And the reason for doing that is you'll see in both terms I have this epsilon. In fact, I can pull out the epsilon as a common overall factor. So let me do that here by just hitting it, putting big brackets around everything. Okay. Now there's another manipulation we can do. You can see more clearly once we've written it down that I can pull out this partial derivative with respect to mu as a common factor. So we can write down the expression and then we'll look why it's equivalent. My claim is that this is the same expression as the above, and you can see that when you apply the rules, when you apply the product rule or differentiation. Okay, so delta mu first of all acts on this term and leaves this one unchanged. Okay, so that's simply what we have here. And then I should leave this one unchanged and differentiate the second term, which is precisely what I get on the second term. Okay, so these two expressions are exactly equivalent. Okay, so now I've got two expressions for delta L. So I've got the one I've just derived, and I had the one I had previously written up here. So let me rewrite it again. Have it on the same line as the other expression. Okay, and these must be equivalent. Delta L must be the same in both cases. What we find, we set them equivalent, or we set them equal rather. We have d mu L this minus all times epsilon nu is equal to 0. So since this holds for any epsilon, the term in square brackets in general must be 0. Okay, so we must be able to set this whole piece equal to 0. But you'll also notice that we have this delta in front of both terms, this partial derivative with respect to mu in terms of both terms. This bit in brackets actually telling me that this must be equal to 0. So we've derived a conservation law, and we've derived a conservation law where this term in square brackets is we're going to call the energy momentum tensor. In other words, we've derived the expression for the energy momentum tensor in terms of the derivatives of the fields and in terms of the Lagrangian. So as I said, this is useful because it allows us to calculate what the energy and momentum are starting from the Lagrange density for any theory. Okay, next we can look at a specific example of calculating what the energy, potentially the momentum as well, what they are, the following from the Lagrangian. So the example we want to look at is this Klein-Gordon equation Lagrangian. Okay, so we have that the Klein-Gordon equation Lagrangian depends on the derivatives of the field minus a half m squared phi squared. And we can use the expression for the energy momentum tensor to find out what the energy and the momentum are. Okay, so let's work out what the energy is. Okay, so I told you that the energy is d3x times the 0, 0 components of the energy momentum tensor. And we have an expression for what the 0, 0 components are. So we just set nu and mu equal to 0. So we need to do d0 phi minus L. And here I've got both indices up. So I have that it's the metric that enters. Okay. So I need to differentiate my Lagrangian, in other words, with respect to the 0, 0 components. So that's, I guess we can write down what our Lagrange density is in terms of the 0, 0 and the I components. Okay, so let's use that 0, 0 is +1 and that the I components is -1. So I is 1, 2, and 3 here. To write d0 phi, 0 phi, minus the I phi minus a half squared phi squared. Okay, so now it's straightforward to differentiate L with respect to d0 phi, what I need to do in the first term. Okay, do that. Okay, so we see that it's d0 phi squared. When I differentiate it, I pulled on a factor of 2, and I am left with simply d0 phi. Okay, that's easy. Okay, so t0, 0 then is going to be 0 phi times d0 phi. Okay, so in other words, I'm substituting in into the expression above. And then I need to subtract off, well, eta 0, 0 times L. So eta 0, 0 is simply +1. Get a 1. And then we can write down my expression for L. Okay, so it's above, just rewriting it out again. Okay, so we get 1/2 of d0 phi squared plus a half I phi squared plus a half m squared phi squared. And of course, I've used here, I haven't been careful about the heights of the 0, because d0 phi is phi dot and d0 phi is phi dot. So in other words, the height doesn't matter for the 0 components. So that's why in this line I've written it simply as d0 phi all squared. Quite often in textbook you'll see it written with the dots on top, so let me write it in that form. So it's a half phi dot squared, it's a half, let's write di as this nabla symbol, so it's a spatial derivative terms, a half spatial derivative squared, and a half m squared times phi squared. Okay, so in other words, my energy then is simply d3x times half the time derivative, half the spatial derivative, plus a half m squared times phi squared. Okay, so that's how we use this energy momentum tensor in practice. So I believe in the problem sets, you will be asked to work out what the 3 components are of the momentum. So pi, p, in other words, px, py, and z. You can discuss those when you go to your tutorials. Okay, we've discussed the Lagrangian density, why it's useful and what you can get from it. So with the Euler-Lagrange equations, you can get the equations of motion. You can also start from the Lagrange density and find conserved quantities. So for instance, the energy momentum tensor. we want to end this lecture by thinking about Hamiltonian density. Okay, so in classical mechanics, we did the Lagrangian mechanics and then Hamiltonian mechanics. Now I want to do, we've done the Lagrange density, and now I want to do the Hamiltonian density. Okay, so let's talk about the Hamiltonian density. So in classical mechanics, you'll remember that the Hamiltonian was a function of coordinate and the conjugate momentum. Now for fields, the Hamiltonian density is going to be a function of the field and of something called the conjugate momentum density. Okay? So I'm going to introduce something which is given the symbol I. So this is defined to be derivative of the Lagrange density with respect to the time derivative of the field. Okay, so this is my kind of generalization of the L u dot that we saw in classical mechanics. So I'm doing now the time derivative of the field. As I said, this is called the conjugate momentum density. Okay, so now my Hamiltonian is now a function of this momentum and the momentum of the field and of the field itself. So it's a function, in other words, of phi and pi. Okay, so now phi and pi are elevated to be on the same platform in the way that in classical mechanics, P and Q were elevated to be on the same platform. Okay, so we have the Hamiltonian, and this is related to the Hamiltonian density. So Hamiltonian density is normally in this curly H symbol. So the Hamiltonian is the integral over all of space of the Hamiltonian density. Hamiltonian density. Okay, so we've introduced two things here. So the conjugate momentum, so it's the derivative of the Lagrange density with respect to phi dot, and then this Hamiltonian density, which is related to Hamiltonian. Okay, and just as in classical mechanics, we could construct the Hamiltonian from the Lagrangian using this Legendre transformation. We can get the Hamiltonian density using the same thing. So now instead of P, we have the symbol pi, and instead of Q, we have phi dot, and instead of the Lagrangian, we have the Lagrange density, early L. Okay, let me give you an example using this Lagrange density that we've been looking at for the real scalar fields. So it's a half mu phi minus a half m squared phi squared. So starting from this Lagrangian, you should be able to show that the conjugate momentum density, in this case, turns out to be just the time derivative of the field, so phi dot, and you should be able to show Hamiltonian density is a half phi squared plus spatial derivative of phi squared plus m squared phi squared. I'm not going to derive it here. I'm just going to quote the result. The derivation is going to be left to the problem. So hopefully you'll be able to use the definitions, okay, to work that out. So we have the definition of the Hamiltonian density, we have the definition of the conjugate momentum, and then it hopefully you'll be able to go from this density, this Lagrange density, to this Hamiltonian. Okay, but that's something to discuss in the problems. That then brings us to the end of this lecture. So let me summarize again the key points for you. Okay, so the first key point is that the dynamics of fields follow from, we saw they follow from Lagrange or Hamiltonian densities. Okay, and these are related to the Lagrangian and the Hamiltonian by integrating over the volume. So the Lagrangian is given L, and the Lagrange density is given this curly L. But as I said, most people will refer to the Lagrange density as simply the Lagrangian. In the context, usually obvious which is which. And then we have the Hamiltonian and the Hamiltonian density. The Hamiltonian density is curly H, and the Hamiltonian is just simply H. Okay. So once we have these densities, the Lagrange density or the Hamiltonian densities, we can get the field equations again. So in particular, we tend to use these Euler-Lagrange equations. So it's the L phi, and it's a relativistically invariant equation, 4-vector notation. So we have on this side simply the derivative of the field, and on this side we differentiate with respect to on this side we differentiate with respect to the field, and on this side we differentiate with respect to the derivative of the field. Okay, we can construct. So often we start by writing down the Lagrange density, but it's straightforward to get the Hamiltonian density using this expression. So it's pi times phi dot minus curly L. And here this pi is this conjugate momentum density, which is dl, the curly L, differentiated with respect to the time derivative of phi. The other thing we discussed was the energy momentum tensor. Energy momentum tensor allows us to work out energies and momentum in the field. So let's write it down in this way with one index up and one index down. This energy momentum tensor can be calculated by differentiating the Lagrangian with respect to the derivatives of the field and subtracting off the Lagrangian. And this is an important quantity, of course, because it's conserved. In other words, it satisfies a continuity equation. Really, 4 separate equations. Right, the first time. It's 4 separate equations here. So the index mu is summed over, and then I have nu as a free index, so nu values 0, 1, 2, and 3. And then we looked at a specific example that we're going to look at in much more detail. We defined the real scalar field Lagrangian. The Lagrange density. This is L is a half d mu phi minus a half m squared phi squared. Okay, and we saw that this leads to the Klein-Gordon equations, the equations of motion that follow from this Lagrange density or the Klein-Gordon equation. And in the problems, you'll have to find or derive yourself the Hamiltonian density, in this case, phi squared plus spatial derivative of phi squared plus m squared phi squared, all multiplied by this factor of half. Okay, so that brings us to the end of lecture 2. So these first couple of lectures we've mostly covered classical physics. The next lectures we'll go on and start to think about the quantum theories. So how to quantize these classical theories.